Thanks very much. I would like, first of all, to warmly thank the program committee to address this audience at the most exciting conference in nanoscience and nanotechnology. So the subject of my talk is quite broad. It's about the emergence of actually metasurfaces as a potential technology to arbitrarily mold optical wavefronts. I like to see things not only point of view of science, but the point of view of technology. So I'm going to talk about flat optics or flat photonics based on metasurfaces. So without a very talented group of collaborators, my graduate students and my postdocs and some undergraduate students, basically none of this would have been accomplished. I view myself like a conductor to some extent, but who's doing the real thing, the real playing, the people who are in the lab doing the real work. I also would like to acknowledge warmly Professor Zhu, Ping Tsai, and Yaowei Wang from Fudan, the University of Fudan, the Academia Sinica, and the National Taiwan University for providing quite a bit of material on the very exciting work that they have been doing, which has expanded further this area of research. So this is an outline. I'm going to briefly compare bulk optics and flat optics. I'm going to talk about metasurfaces, and in particular how you can mold light wave propagation using phase discontinuities. Some people mumble when they hear phase discontinuity. There is not a discontinuity, of course, in physics, but we talk of abrupt change of the phase over a distance small compared to the actual wavelengths. That's what we mean by phase discontinuity. We have demonstrated in this sense generalized laws of reflection and refraction. We have done some experiment. And a lot of the talk is about talking about really the richness of metasurfaces. I will not only cover metasurfaces where the key element is a spatially varying phase response, but also spatially varying polarization. And the last part of the talk is about flat optical components, quarter wave plates, flat lenses, vortex plates. And I want to bring you some of the very latest research from my group about holographic metasurfaces, generation of vector beams using radially polarized light. So the question is, can we replace optical components with actually flat ones? When I mean flat, I really mean flat. You know, in this sense, diffractive optics, I don't call it flat optics. You know, the ones where you all these indentation and actually so forth, where we have a really structured interface. Here, everything is basically on an actual plane, okay? And we have a single optically thin sub-wavelength structure surface, which we call metasurface. Now, we cannot talk about this area of work without talking about metamaterials in general. This is a very broad summary of many years of work by pioneers of the like of John Pendry, Dave Smith, and Victor Selago, where using concepts of metamaterials and transformation optics, they show that basically you can engineer the optical path of light in absolutely counterintuitive ways. And for example, you can achieve negative refraction, and you can achieve also optical cloaking, which is to learn how to use in real time this thingy here. That's it. Just use the traditional methods, optical cloaking. So now the question is, can we do this in actually 2D? So I'm going to talk about metasurfaces. And there is a good reason to do it, basically. See, planar technology is central to electronics. We all know that is a $300, $400 billion industry. It is a technology platform. My claim is that because of fabrication complexity, 3D optical materials do not have a good chance of a major technology impact. I mean major, large scale at optical wavelengths. There is certainly beautiful physics, but limited application and hard to make in a simple way, fabrication tolerances, yields, and so forth. So we should be looking at 2D structure, and particularly optically thinned, engineered surfaces, so that we can achieve arbitrary wavefront control. Now let me say, I do not believe that the refractive index is a necessary and particularly useful quantity. That's my point of view when we think about metasurfaces. Well, we can go straight directly in engineering locally the phase, the amplitude, and the actual polarization along the surface using optical resonator. So we can make a class of optical components. And standard optics works on three-dimensional phase. I mean propagation phase is just the integral of the refractive index times K0. Okay, here's the main concept, okay? Take a surface, take a regular surface. If it's not structured, light that comes normally is transmitted through, but you need to understand this physically in terms of Huygens principle, that every point along the surface creates a spherical wavelet, and you take the envelope at the next delta t, or actually delta x, and so that's how you create the wavefront. Now, what if I have an homogeneous surfaces? What if I put here locally resonator, a distribution of resonators in an optically thin surface, much less thinner than the wavelength, the interface, and the resonator are sub-wavelength space, and I locally change the geometry of the resonator? What happens? Continue to apply Huygens principle, you see that now I can mold any wavefront I actually want, depending on the individual design of the antenna. The key point you see is the phase response here. The antenna introduces the antenna or the resonator, more in general, scatters the incident light by changing the amplitude and the phase in particular, and maybe the polarization also. In particular here, it's important the phase control. See, so each resonator introduces basically a phase jump here into the light wave that propagates. That's what we call biphase discontinuity. And so now we can say, what if I have a so-called gradient metasurface, okay, where I have a distribution of sub-wavelength space resonator with the phase response as defined before, okay, where the gradient is actually constant along the surface. What happens then if I want to study phenomena of reflection and refraction? I just apply Fermat's principle that says that the path of light is that of stationary phase, which means that two infinitesimally closed paths have to have a phase difference of actually 0. And now this phase contains a propagation part, which is in dotted line, and at the interface there are this phase jump. So here how I impose this phase condition, and then it's very, here pops out the generalized law of reflection, okay? In addition to the ordinary term of Snell law, I have this phase gradient here, which can interpret it effectively as a wave vector that allows to generalize the law of wave vector, parallel wave vector conservation. You can use alternative language of phase matching, whatever. There is also a generalized law of reflection. It means the angle of incidence is no more equal to the angle of reflection. And so I can get both anomalous reflected beam and anomalous refracted beam. And now what happens is this assumes that the plane of incidence contains the plane of the resonators is in the plane of incidence. What if there is an angle between the plane of incidence and the direction, the rows, if you like, of resonators? Then you can get an interesting variation on this phenomena. You can get basically that the anomalous refraction, for example, can be out of the plane of incidence, which is very interesting, and we have explored these in this actual paper here. Okay, so now how do we do this abrupt phase shift? How do we make this resonator? We have a lot of choice. You can use not only, people have said, oh, you're talking about only optical antennas. No, we have made it very clear in our papers. You can use basically any kind of resonators, dielectric resonators. You can use quantum dots. You can use nanocrystal. We are focused, because at home we have these technologies for a number of years, in optical antennas. The important thing is the requirements, actually, and the requirements are, again, this is already covered. You see, if you want to control the wavefront, you want to have really 2 pi phase coverage. This is very important. And to achieve that anomalous reflection and refraction, meaning transforming a plane wave into a plane wave with almost arbitrary angle in reflection and refraction, I need high and uniform scattering amplitude across the elements. So we use optical antennas, basically, that are, if you like, are metallic nanoparticles, and they can achieve all these things in quite an elegant way. So I'm going to show, this is elementary. Let's talk about a simple antenna. Is a linear thing here of length L, and it has an amplitude and a phase response. And we know here in particular what I want to plot is the phase and the amplitude response as a function of the length of the antenna divided by lambda. This brings home the message now that for a fixed lambda, if I change L, I can actually vary the phase over actually significant range, and of course the amplitude. Is this principle used? Look, folks, we are conceptually in the context of metasurfaces, of transmitter rays and reflector rays from the microwave millimeter wave field. However, and that's what they have, because we are jumping wavelength range by orders of magnitude, there is significantly interesting new physics and some also novel aspect in the actual technology. In particular, we really go into the sub-wavelength regime and so forth. Just what I said, you see, the famous Yagi-Uda antenna achieves this nice beam shaping by essentially using the principle here that you vary the actual length here, you see, and by vary the actual length, you can vary the phase response because you're operating at a particular frequency. So this is the context that we are. I mean, we are in a concept which leverages in part on the work of years on phased array antennas in microwave millimeter, but expands it up to the visible range, near infrared, and so forth. And this is our first thing that we looked at. This is a paper that has had it really mushroomed the consequence of this paper. There have been hundreds of citations and really a lot of follow-up by many groups that I will try to capture. And basically, see here, this is basically a phased antenna array in the actual mid-IR by which we demonstrated this generalized law of reflection and refraction. So the key element here is this row of antenna. We use V antennas. The key point are what? Besides the one that I said before, the 2 pi phase coverage. In other hand, in going from here to here, there is a 2 pi phase shift in the actual scattered light. And the advantages are, there are also some advantages that are pretty here and quite obvious. Now, this is not the only antenna, type of antenna. After our work, there was, again, a lot of activities on metasurfaces. Here on the right is an example, our example of metasurfaces which use a metallic backplane at a sub-wavelength distance. Okay, so this is actually to make an efficient reflector ray, first in microwaves, and then done at actual near-infrared wavelengths with efficiency up to 80%. And they all have this, you might ask, how do you get the 2 pi phase coverage with such a simple linear antenna? And I will explain it shortly. So this is ours again. So the experiment is basically, this is designed for the mid-infrared. We come in with an incident wave and we study the anomaly of reflection and refraction, and it's optically thin, 50 nanometers and so forth. And for example, if we do full wave type of simulation, we find for normal incidence, this is how the wave, the scattered wave looks at, and this angle precisely is what you obtain with a simple argument of actually Fermat's principle. And you see the Huygens principle, even though it was created 100 years before Maxwell's equation, works very well. Okay, this very intuitive principle. And now I want to say something about the V antennas. Again, you know, the V antennas are not new per se. Okay, if you're old enough like me to have seen Sputnik, you remember that Sputnik had a V antenna. They are on TV sets. Okay, in more the modern concept, Professor Želudev, the next speaker, wrote an applied physics letter years ago where he analyzed the interesting symmetry and anti-symmetry properties of this V antenna. This is what I want to now focus a bit, you see. They allow a versatile manipulation of the amplitude and phase. They are inherently broadband. You see, you have a symmetric mode of oscillation of the current and an anti-symmetric mode here. One length scale here is L. In this length scale is L, and this is half. I mean, there is a factor of 2 in the relevant length scale, so the two modes have shifted roughly by a factor of 2 in actual wavelengths. You can treat it like harmonic oscillators that re-radiate, that actually scatter light. And for example, this is the scattered intensity as a function of wavelengths. Now, let me say something. I mean, when you want to use antennas for molding the far field, the wavefront, they can't be high Q. Sometimes there is a misunderstanding here. They have to be low Q. They have to have high radiative losses. Okay, this is very important. Okay, and moreover, the fact you have two modes allows you to achieve polarization conversion that allows you really to do the 0 to 2 pi phase shift necessary for complete control of the wavefront. You can see that in fact the phase response really is significantly larger than actual pi as a function of wavelengths. And so I don't want to spend too much time on this, but how do you get the phase carriage? First of all, in this first type of experiment, we were coming at incident polarization in between the symmetric and the anti-symmetric mode. And the scattered light comes out from a linear combination of the fields of these eigenmodes. Okay? So now we start first, we can vary in this way the phase from 0 to basically pi, okay, by changing the actual angle and the actual length, as you can see. You go from linear to this here. Now, how do you get the 2 pi coverage? First of all, let me tell you that for this geometry that we come with the field exactly here, the scattered light is cross-polarized with the incident field. Okay? So what happens is, the way you achieve the extra pi phase coverage, you take the mirror image of that. Mirror image means in terms of the actual currents that the horizontal component of the current, which is really the one that creates the actually scattered field here, is flipped by pi. So with this trick, we achieve completely coverage from 0 to 2 pi. So this is one way to do it with V antennas and so forth. And these are the experiments that will, and normal incidence, you can see very clearly this that follows the anomalous, the new law, generalized law of refraction. There is nothing here at this other order. So you can say, what is this? How does this relate to an actual grating? There is another point of view that you can say that this metasurface functionally, but only functionally is actually acts like a blazed grating. Essentially, you have engineered the scattered field so that you get nothing at this order here. Okay, but of course we use phase the discontinuities, so we don't use the propagation phase used in sort of, if you like, conventional blazed gratings and so forth. So this shows that it's broadband for the reason that I said before. So actually this scatters anomalously refracts from 5 to about 10 micron, which is interesting. And now we can study this for different incident polarization. And if you come in with an angle of incidence that is not exactly at 45 degrees between the symmetric and the anti-symmetric mode of the antenna, what you get is that the light that comes out will not be cross-polarized, but the electric field of the scattered wave will be at some angle which is not 90 degrees from the incident thing. So this is the analysis of the polarization of the scattered wave depending on the incident polarization. Of course, the angles of scattered are always given rigorously by this generalized law of refraction. And reflected and refracted, here's the thing. What is the efficiency of this? It all depends on the design. Of course, it's not too high. As there are three factors here. There is a polarization conversion, so you lose some efficiency. Okay. Second, you have both a refracted and a refracted beam. Okay. Third, there is the filling factor of the antenna. Now, the filling factor can be improved. In fact, you can use mutual coupling between the antennas. And but fortunately, there are other strategies where you can actually considerably increase the efficiencies, and I'm going to talk about these. Okay. First, let me say that this work was generalized by the group of large Shalev and near-infrared wavelengths, where they showed broadband light bending from 1 to 2 micron wavelength. And now I want to tell about the groups that I cited at the beginning. These are groups at the University of Fudan, at the National Taiwan University, and the Academia Sinica, which they have addressed the issue of the efficiency, and they have looked particularly at making reflector arrays at visible wavelengths, starting actually from microwave using these concepts of gradient metasurfaces. Okay, so here is so the point is this, okay, you make a sub-wavelength spaced metasurface here, and you put a metal sheet here at actually sub-wavelength distance. What is the purpose of the metal sheet? Okay, well, of course, it cancels the transmitter component. That's kind of trivial, but important. The important thing, there are several ways to look at this. Even though these are simple antennas, basically you'll see with just one dimension, roughly, okay? They look really like linear antenna because of the interaction with the metal plane, okay? You get a near phase coupling that allows you to to get a 2 pi phase change. There is another way to discuss here, but I don't have the actual time. So again, you come in now in incidence, and you're looking at ordinary reflection, and you actually maintain. You have these are two. You always have, of course, the ordinary reflected and the anomalously reflected beams. So this was initially done by the group of Fudan. You see in the actual microwave, they made this H-shaped antennas here. Again, you spatially vary their shape here. There is a metal backplane here, and you see the phase response. They're able to get a nice 2 pi linear phase shift. And then they could study beaming. You see, they could study clearly these directed reflection, these anomalous reflected channels. And in fact, by designing correctly, they were able to get 90% of the light to be redirected into the anomalously reflected beam. And so this actually is this is interesting. It's in the microwave region. So it's an interesting case where also the microwave experts can learn from our developments of transmitter arrays and reflector arrays at shorter wavelength. And now here's the question: is it realizable at optical frequency? Yes, and there's been some beautiful work done by the groups that said before, and this is the actual structure. You see, essentially they look very much linear type of antennas, but because of the interaction with the substrate here, you can still get the 2 pi phase coverage. So you come in, let's say, at this incident angle normal, and you anomalously reflect this way. You can see here the working wavelengths were around 800 nanometer, and this is how the subcells were made. Okay, the subcells. We have a gold rod. We have a magnesium fluoride spacer. That's the dielectric. Okay, and we have a back gold film. Okay, so so basically the phase, the spatial phase change, you just vary L. An important thing here, we are looking for response for polarized light along, of course, the resonance, if you like, along the long dimensions of the antenna here. If we want to show this anomalous reflection, if we polarize it in the other direction, X, we basically do not, we only see the ordinary type of reflection. And so these are actually the data, which I think are quite impressive. This is the experimental setup. So we have here the measured and the simulated normalized scattered electric field in density experiments, FTD simulations. You see for different angles of incidence here. And the key point is that the normalized scattered field peak of the anomalous reflection in the anomalous reflection channel is basically 80%. Okay, so there is the message to take home. You can make efficient gradient phase metasurfaces, certainly in reflection. Other groups are working in transmission also, in particular using dielectric resonators. I'm going to say something, there's just limited time. One cannot cover all the enormous amount of work that has occurred in just the last 2 years. And now this is a very interesting point, okay? So again, these are the data actually from those metasurfaces. You see, this is the angle of incidence here, and this is the reflection angle. So clearly you can see the anomalous, in this region you can see the anomalous reflection, okay? Now what happens? You see at some point there is a critical angle. Yes, there is a critical angle above which there is no more reflection. This is the interesting path. So energy must go somewhere. We pointed that out in our first paper in Science. We did not expand it. This group really expanded a lot this concept and actually showed that you have surface wave that propagates beyond this point here. Now this is a talk about the far field, the wavefront. I don't have time to cover it, but they did beautiful work using near-ensom techniques, near-field scanning optical mirror, to study this surface wave. The significance, these are really new surface wave, because you see the surface is not spatially homogeneous. This is the important point to bring home. So these are not surface plasmon, these waves, okay? These are simply new types of surface wave that are based on these actual phase gradient. And one thing that I want to point out that in the regime here, before you start to launch the surface wave in this regime, you know, again, a simple way to interpret this generalized Snell law is just by momentum conservation, right? This is incident wave vector, and you get essentially a phased term, okay, a gradient, okay, that allows you still to conserve the lateral wave vector in actual scattering. But I want to point out this is a very rich area of studying these surface wave. There is a tremendous amount of work to actually do. Okay, broadband type of operation. This works with from 750, you know, to about 1 micron, and so forth. And again, the field, the scatter field, transforms into a surface mode about a critical angle for which there is no more reflection. Well, this is basically a summary of this, so I don't want to. I now want to start to talk about components here. So the summary is that so far we have shown there is some really interesting physics from these generalized surfaces. And now the question, what can we do with it? The first thing that we looked at was a meta lens. A meta lens, essentially a flat lens that allows you to create a spherical wavefront, rigorously spherical for all angle of incidence, and so has no spherical aberration. This is this paper here, so the key point is this, you see. If you want to have a flat surface, how can you create a spherical wavefront? You have to decorate it with actually resonator. And what you have to make sure, you see, the phase shifts. If you only use propagation phases, it's a no-win type of situation, because the propagation phase from this point to this point is different than from any point, let's say, inside this circle or actually outside. Okay. However, what we want is that the phase, the total phase difference from this point to here is actually the same for every point of the surface. So how we do this? We have to essentially compensate this varying phase shift. You see, this part of the phase shift from the sphere centered in the focal point is actually the same for every direction. That's obvious. Okay, so now we have to, at each point, we have to have an antenna designed such that it creates an abrupt phase shift that compensates for the difference in propagation phase shift from this point here to here. And if this is done, it's very simple and elegant. You show that the XY distribution of the phase, the in-plane distribution of the phase shift has to be an hyperbolic and this type of function here. This is, by the way, so what does this done? This compensates completely for spherical aberration. You can make very high numerical aperture lens, okay? What it does not compensate is for chromatic type of aberration. Recently, the first author in my group, however, with a paper just about to be submitted, where he has shown that you can design, if you design this meta surface with some curvature, you can actually do a very significant compensation of the chromatic type of aberration. This meta lens suffer from an efficiency problems. The group of Alu, Professor Alu, has shown that if just with 2 or 3 layers, you can increase quite a lot the transmission efficiency. Now you can also decrease the actual spacing. So even as a transmit array, I think there is a lot of improvement to do. There's still a lot of space for improvement to make these for these meta lenses. I should say there has been parallel work by the group at Hewlett-Packard by Flatal et al. On dielectric meta lenses, if you wish, that use dielectric structure and use the same phase distribution to achieve essentially a lens without spherical aberration. Now I want to move to a broadband quarter wave plates. We've been asking the question, how can we design like a quarter wave plate or any kind of actually wave plate by using these concepts? What could be the advantage? Well, the advantage is, for example, you are background free because you come here and you scatter off here, for example, in circular or a elliptical polarized light. So the key design must be pretty clear, the principle. The single unit of this quarter wave plate contains 2 elements. One, they create the two components of the amplitude that have to be the same amplitude and a phase shift of 90 degrees in order to create a circularly polarized wave. So the way the amplitude design is straightforward. How you get a 90 degrees phase shift, you essentially, this is how you actually control the phase shift, if you like, by sliding these 2 units. This is a phase slide that is exactly 90 degrees. So that now that the 2 components, you see, the two components that are created, designed to have same amplitude and 90 degrees phase shift. We have shown that it's a nice broadband for 5 to 12 with a high degree of one polarity of polarization. For example, you can have a ratio of almost 1,000 between, the polarization that you want and the unwanted one. And these, in fact, are the actual data. Again, I explained already this, how it basically works here. And with a polarizer, with an analyzer in front of the detector, one can analyze the degree of circular polarization, and we can say that we are really satisfied with this. Is basically circularly polarized light from 5 to 10 micron, and the degree of circular polarization is indeed extremely high. Okay, and now I want to go into the last part, is about sort of creating strange beams. Strange beams. By strange beam, I mean sort of non-conventional. Last Photonic West, Mike Padgett, who is really one of the big pioneers of vortex beams, he gave a beautiful talk on create optical vortex. See, the optical vortex is a beam that has a spiral wavefront. Okay, and so the energy spirals around the direction of propagation, the Poynting vector, with a phase factor here that describes the vortex given by this. If you have energy that rotates around the propagation direction, you have orbital angular momentum. So photons actually can have do not only have spin angular momentum, but in certain types of wavefront like this, they have an orbital angular momentum. This was recognized as early as 1930 by Darwin, pioneer of quantum mechanics, and by Dirac lately, who tried to explain is how can we have forbidden transition in an atomic system where the angular momentum jumps by a factor of 2, extremely weak. Well, what does it is this, is the orbital angular momentum. Okay, in these transition, actually the emitted light has a non-conventional wavefront, like an optical vortex. These are so-called Gauss-Laguerre polynomia, okay, and they are characterized by the fact that as you increase the orbital angular momentum, you develop these regions where the intensity goes exponentially down to 0 at the center, and the phase is actually indeterminate right at the center. I want to define here that the orbital angular momentum is the number of twists of the wavefront within a wavelength. That's the definition. And the interest has been exploding. Alan Wilner recently has published some beautiful papers on doing light transmission with optical vortices to encode information and so forth. You can create them with spiral phase shape, with 4 gratings. You can create them the most powerful and general ways using spatial light wave modulator. We have concentrated in particular the work of the inspirist Patrice Genevet in my group, who has figured out a wave. We can use a metasurface to create a phase, a vortex plate. And the trick here is to have sectors, and each sector introduces a pi over 4 phase shift. So you can design this to have any number of sectors to have L equal 1 vortex or an L equal 2 vortex and so forth. So it's the metasurface that imparts right at the surface, and this we showed by actual simulation, that within a sub-wavelength distance from the metasurface you have the fully formed vortex. And so this was the experiment done with a quantum cascade laser. You come in with TM polarized light, you are incident on here, and then if you don't have this arm here, you look in an infrared camera, you will actually see a vortex. But that's not enough. The vortex tells you the intensity information. You want to hear about the phase information. So you have to do an interference experiment and deviate the beam here and combine it here. If these beam splitters are such that the 2 beams are actually collinear after the beam splitter, you will see a spiral. If not, you'll see a dislocation of the field, and you can intuitively understand this in a very simple way. I mean, I'm actually adding, let's say I assume that these two beams that recombine are collinear. One is the original beam from the actual laser, a simple beam with a curved surface. It could be typically a Gaussian beam, and that actually interferes with what? With a spiral wavefront. And so the interference you can see from here, the intersection, which is the points of equiphase, must be a spiral. Okay, and of course, depending on how you design the metasurface, okay, you can have a spiral one way or the other. These are actually data from our experiments. And now, what happens if you tilt them? This is fascinating. If you tilt them, actually, this goes back to pioneering work by Michael Berry of Berry's phase fame and many other things in physics. You can create a dislocation fringe of the electromagnetic field, which this is actually quite beautiful. Okay, and so we have studied this. This again is the work driven primarily by Patrice Genevet in my group. This, for example, is a metasurface which creates a 2 pi phase shift. So if you like a vortex angular, a vortex beam with an angular momentum of unity, either +1 or -1. If you tilt, again, the two beams, as I showed before, you can easily see this dislocation, and the dislocation contains the information on the topological charge of the vortex. The topological charge is a slightly complicated way to define the orbital angular momentum. If you make a metasurface with a 4 pi phase shift, you have +2 or -2, and so forth. Now I want to tell you about something actually quite interesting here. Okay, see, before the metasurface was, the key point was using the dispersion of the antenna, the dispersive property of the antenna to create the phase control. But there is a completely different way to achieve this phase change. And this is what? It's to use a so-called Berry-Pancharatman phase. So it's the phase change related to the change of polarization. So these are tiny apertures, as you can see here, right? Let's say sub-wavelength aperture, and here also you see what happens is you see they're all the same shape. The orientation changes. Okay, so this is the key point here that I'm going to try to explain kind of intuitive. So you can treat this aperture basically like tiny polarizers, okay? And if you use a Jones metric formalism here, typically used to treat polarization, okay, the transmission through this, okay, I got it. The transmission through this actually, you see, contains this phase factor here, alpha, okay, and this is basically equal to what, this alpha? To the orientational angle of the aperture. That's the important point. Okay, so there are two examples here. Okay, so if you change, again, because of this, if you change now the orientation, then it should be clear, like if you come in with circularly polarized light for this here, okay, you actually create a mapping between polarization and phase. And the first example is a vortex beam, and the second example is actually a flat lens, okay, that can focus what? Can focus circularly polarized light, okay. So it takes a while to get familiar with this way to do the phase control, but it's certainly very interesting. It has some very interesting type of applications. Okay, this is yet two other beautiful example of this by these groups here, okay? And the first one is what? Rod antennas. You see, the rod antennas are the same, but the orientation changes, okay? And it can generate over a vortex beam over a broad wavelength range. I can show it here. Why is it broadband? Because the phase shifts. The phase distribution comes from the antenna orientation, okay? And basically the structure is actually dispersionless, okay? The second is actually I would say we can call it very cool. And basically, it is an actual lens, okay? And it basically beams, it's not a lens, it beams a circularly polarized light in different directions, okay, depending on the actual degree of circular polarization, where you are plus sigma, +1 or -1. So again, I hope these last few slides showed that these concepts can be generalized, and you do not have to use dispersion also. You can use other things, okay? So I know I'm close to the end here. So I want to conclude. There is going to be a talk here given by Patrice Genevet at this conference here, so I really don't want to steal the show, but if anything, give it some exposure. We have been asking the question lately, using holographic technique, can we make elements, optical elements, that can locally change not only the phase and the amplitude, but also the polarization, so that we can create interesting vector beam. And this is the last paper of my group showing actually how you can do that using these 4 holograms. You see where there is a sub-wavelength structure here. Okay, so the sub-wavelength structure controls the actual polarization, as you can see it. And I'm just going to show you a few things. This is a generalization of the famous detour phase hologram concept, where we are adding the component of the actual polarization. Okay, so I want to fast forward here and show you how basically, so the hologram is basically done like this. You see, it is a hologram that combines a circular groove, sub-wavelength space, and an actual fork, and the net effect, you create a truly radially polarized beam. Okay, donut shape here with this intensity profile and radially polarized, and it works very well. Finally, here there is a structure that everyone can see of this very interesting holographic, we can call it, yes, certainly as a metasurface in a general sense, and we're coming in with the polarized light and circularly polarized light. Okay, one can create radially polarized beams, and one can analyze and see really they're radially polarized and they're broadband. So basically, this leads me to the end of my talk. So metasurfaces are powerful ways to think about transformation optics. You can call it as folding of optical space. You do the folding at the interface, and you create kind of an optical type of origami, as we illustrated in this here. Phase discontinuities are a very useful concept to treat, to understand scattered wavefront, and we have demonstrated these applications here. And now I want to tell you, what is the connection with, tradition? Obviously, there is a connection with diffractive optics, and we have been interacting with a lot of the experts, in particular lately with Bernard Kress from actual Google. Google is actually doing quite a bit of optics, and he told me how he thinks about this. Well, he thinks it's really the technological simplification, because of the metasurface thing with a single digital pattern, which is one mask level, you can create an arbitrary analog phase profile. And the lithography, well, we are doing with e-beam lithography, but around the corner for optics, I'm a believer nano imprint will come, and there is also soft lithography coming. And so this is almost the last. So what is the vision of flat optics? I think it's not going to happen kind of overnight. I have a lot of experience having worked at 25 years in industry before. Things do not happen kind of overnight, but I see a bright future on a length scale of 5 to 10 years for a new class of flat components, broadband, and so forth. The ultimate thing is to do high-speed, tunable phased array for real-time wavefront control and any wavelengths down to the visible. That's really the holy grail. Applications are as wide as smartphone. I remember when we got the flat lens to work, a company called me and says, when are you going to make this practice? I said, well, why is this important for you? This was a phone company, and they said, well, can you make a a smartphone as thin as a credit card. Then I understood. There is a lot of potential in the actual mid-IR where there is pure refractory optics, high numerical aperture type of objectives, putting stuff on stretchable materials, biomed application, you name it, is actually quite exciting. I want to conclude by thanking my group here. This is our group, which is anomalously reflected, you know, so we at least can have some fun with it. And so thank you very much for your attention.